Hi all, hi all. Welcome to the video lectures on VHDL. This is the second video lecture, and in this lecture, I am going to cover uh, full adder, uh, realization of the full adder using VHDL, and specifically, I am covering the behavioral modeling of full adder. So in this video lecture, I will try to cover two different ways of writing the full adder in the behavioral itself. So carefully follow the lecture and make a note of the things before coming to the lab. So as I told you in the last lecture, before we start the programming in VHDL, the first thing what we should do is make ready with the block diagram, truth table, equation, and the schematic diagram. So here we are trying to realize full adder circuit. So this is the block diagram of full adder. This shows it is having three inputs A, B, and C in, and two outputs sum and carry out. And this is the truth table of full adder, showing the relation between the inputs and outputs. And here this is the equation for the output, means output equations for the full adder circuit. Equation for the sum is A XOR B XOR C in, and the equation for the carry out is AB plus BC plus C in. And next, this is the circuit schematic of the full adder using these equations. You can see here A XOR B XOR C will be giving the sum, and AB plus BC plus CA will be giving the carry of this. And another way of realizing this full adder is by using two half adders. So here you can see we can get the output of a full adder through two half adders. So here you can see that from one half adder uh, and here it is another half adder. By proper connections between these two half adders, we can get a full adder realization. So in the last video, whatever I covered is the data flow model for the simple AND gate. There I told you that for the data flow, we can simply use these equations in the architecture to realize the structure. The same thing can be followed here. Suppose if you want to realize a full adder using a data flow, the simple thing you can write in the architecture is sum is assigned with A XOR B XOR C, and C out is assigned with A and B, or B and C, or A and C. So these two lines will be giving you the data flow model of the full adder. So the first thing to be noted here is for writing the data flow modeling, you require the equation and the output equations of the circuit. Whereas now in this lecture, we are trying to design the behavioral modeling. For designing the behavioral modeling, we require the truth table, and according to the truth table, we will be designing the behavioral modeling of this full adder circuit. So as I told you, there are three inputs A, B, C in, sum and C out are the outputs. So now let us see the programming of the full adder circuit, and the remaining schematics will be covering in the structural modeling that we'll be covering in the later videos. So now in this video we'll focus on the behavioral modeling. So this is the program which we are going to discuss now. So initially, this is the first type of realizing the full adder using the behavioral modeling. You can see here we are taking three ports A, B, C in, and sum and carry as the outputs. And the behavioral modeling consists of a process. So you can observe here, after the architecture, after the beginning of architecture, you can see the process, and in this process we are sending the inputs. So this is called a sensitivity list. And once the process is started, after the process, you will be writing the begin, and here you will be writing the if conditions. If A is equal to 0 and B is equal to 0 and C in is equal to 0, then sum is assigned with 0 and carry out is assigned with 0. From where we are getting these things is from the truth table. So observe here, when A is equal to 0 and B is equal to 0 and C is equal to 0, then sum is assigned with 0 and carry is assigned with 0. So like this, each line of the truth table will be coming in this behavioral modeling. And one more important thing before we go into the Vivado is, so here multiple conditions are there. If else if ladder will be using, if A is equal to 0, B is equal to 0 and C is equal to 0, then the first row will be coming sum is assigned with 0 and carry is assigned with 0. Else if, please make a note here, else if the spelling is ELSIF, else if the second row of the truth table, and else if. So this else if will be continuing until the last but one column, 110, and the last case will be just using the else. Means if the above conditions are not satisfied, then we will be getting sum is equal to 1 and carry is equal to 1. This is the last line of the truth table. So from this we can understand that for means for realizing a structure, for realizing a logic using the behavioral modeling, truth table is important. So now we'll try to simulate this program using the Vivado. So double click on the Vivado software. So double click on the Vivado software and wait for the system to respond. And once the system is opened, you will be getting the window like this. So click on the create project. Next, so here I am saving, giving the project name as Full Adder 1, and I am saving this in the D drive. So whatever the folder I am using for this demo, the same folder I will be using. So here the demo VHDL program I am selecting, and I will be saving these programs in that particular folder, right? So FullAdder 1. Next, click on the RTL project. Next, before using means clicking on the create file, target language is VHDL and simulator is mixed. Create file, and here the file type is VHDL and the file name is FA1, FullAdder 1. Okay, then click on next. Here we are not adding any constraints. Next, and in the default parts, convent means in our lab we used to select Arctic 7, CSG 324, speed is -1, temperature is C in our lab, but here we used to select all remaining, and we are just selecting the default part as CSG 324-1. Create on the next and see the summary and click on finish. So once you are doing these steps, you will be getting a window, and it will be asking for the inputs. So here I am giving the inputs A comma B comma C in are the inputs, the sum comma C out are the outputs, and click on OK. Because I am using the behavioral modeling, I did not change the architecture name. Click on OK. After clicking OK, you can find under the design sources we can find the VHDL code with the name what we gave in the previous step, FA1 behavioral. Double click on that, then we'll be getting this window, the workspace where you used to type the code. So as I told you in the beginning of this video that for this behavioral modeling, we used to write the process, and from the process we'll be following the steps, means we'll be following the lines of the truth table, and accordingly we'll be typing the program. So before starting of the program, one more important thing you should remember, everyone should remember, is we should add few libraries here. See, generally we'll be getting the default libraries as library IEEE and use IEEE.std underscore logic underscore 1164.all, and along with that two more packages or libraries we are using, that is std underscore logic underscore unsigned.all and IEEE dot numeric underscore std dot all. So after adding these two libraries at the header, then we'll be going for this architecture. After this architecture, we'll be typing the process and then we'll be beginning the process. For the sake of saving the time, I'm going with this code. Whatever I showed you, I explained you in the beginning of the video. So after begin, we'll go for after beginning of the architecture, then we'll go for the process, and the process will take the inputs a comma b comma c in are the inputs. So here you can see the process we are sending the inputs as a parameter. This is called a sensitivity list. And then begin. After this process, we are beginning the process, and then here you can see if else if ladder. The first line of the if is the first line of the truth table, and whatever the outputs we are getting, we are just assigning. Make sure that if a is equal to 0, 0 should be in the single quotes. So whenever you are assigning the numerics, that should be in the single quotes. So following the truth table, we will be writing the if else if ladder, keeping in mind that last but one row of the truth table will be ended with the last else if, and the last line of the truth table will be coming with else. So last line is like if a is equal to 1, b is equal to 1 and c is equal to 1, then sum is assigned with 1 and carry is assigned with 0. Then after that we'll be ending the if, end the process, and end the architecture. So the default name whatever we gave here is the behavioral. So this is how to program using the behavioral modeling. Then after typing this program, press Ctrl S, save the program, and follow the steps for getting the outputs. Like what I told you in the video one, first video. So first we'll be going for run simulation, run behavioral simulation. Run behavioral simulation, we'll be getting the waveforms, and after getting the waveforms, go to the each steps, each of the inputs, ABC, and right click here, give the inputs. Here you are having three inputs. So force clock, radix is binary, leading edge is 1, trailing edge is 0, cancel after 2000 nanoseconds, and the time period is 100 nanoseconds for the A. And for the B, right click, force clock, radix is binary, leading edge is 1, trailing edge is 0, cancel after 2000 nanoseconds, and here because we are having the same time period, we are just changing the time period to 150 nanoseconds. Similarly, here we are having the third input, do the same procedure, force clock, radix is binary, leading edge is 1, trailing edge is 0, cancel after 2000 nanoseconds, and time period will be different than the above two, that is 200 nanoseconds, and click on OK. Click on the run button and you can see the outputs. So if you want to see the outputs, you can click on zoom fit and you can undock this window and just expand this window, and you can zoom it, and by placing this cursor, the yellow cursor, you can verify the truth table of the FullAdder. So this is the first step, and one important thing I will be telling you here is, so once we are simulating this, the next step is I will be going for open elaborated design and click on OK. The RTL schematic will be getting here in this step. So in this step we are getting the RTL schematic. So wait for the system to finish the process. So after this completion of this, you will be getting the RTL schematic. So this is the RTL schematic what we are getting here whenever we are writing the behavioral model of the full adder using the direct A, B, C in, means whenever we are taking the three inputs and we are using the if else if condition. Please make note of these things, and in the first video I told you very clearly how to take these printouts and how to see the various outputs. That is common for all the circuits. First you should go for simulation, run simulation, behavioral simulation. You will be getting the waveforms, and from here you should take the schematic, and after that you will be going for the run synthesis. Then the synthesis report will be coming. That you can refer to my first video. And here in this video we are just focusing on the behavioral modeling of this full adder circuit. So this is the first way of behavior designing a realizing a full adder circuit in the behavioral modeling. And now I want to tell you the another way of realizing the full adder in the behavioral model itself. So just I am closing this. um, I will start the new Vivado, and before it opens, so just I will explain one more program. See here, we are just taking the input as A, and unlike the previous case where we are taking A comma B comma C in as an inputs, here I am taking the A, which is std underscore logic underscore vector 2 down to 0. What does it mean? It means that we are taking a 3-bit input. 0, 1, 2 means A is of 3 bits, and output O is of type output. It is also std underscore logic underscore vector 0 1 down to 0 means it is output is of 2 bits, 0 and 1. So here, instead of taking the 3 bits and the 2 bits for the inputs and outputs, we are directly taking the std underscore logic underscore vector. And the process is the same, but instead of using the if condition, we are using the, even here we are using the if condition, but instead of giving the condition as A is equal to 1, B is equal to 1, and C is equal to 1 in all the cases, we can directly compare this as you can see in the screen. So we will try to realize this same in the Vivado, and we'll see the differences. So again, the Vivado is opened. Click on create new project. Next. So here the location is D drive demo VHDL projects, and here I'm trying to give the name full adder 2 because previously I gave full adder 1. Next, RTL project. Next, uh, target language is VHDL and the simulator language is mixed. Create a file VHDL FA2. I am giving the name as FA2. Okay. Next, the default parts family will be selecting Arctic 7. Package is CSG 324. Speed range is -1. And in this case temperature and static powers we are not selecting, and just we are clicking on the CSG 324-1, the same procedure what we followed for the previous one, and finish. Once you are clicking here, uh, uh, so the workspace will be opened, and here you are getting the entity name whatever we gave, and the same realization we are trying to realize in the behavioral model. Now observe the difference. So previously I gave A comma B comma C as an inputs, but here I am giving A as an input, and I am clicking in this bus, on this bus, to specify that MSB is 2 and LSB is 0. So this is the main difference between the previous program and this program. So instead of giving A comma B comma C in, here I am giving A of type input, and this is of type logic vector. So for representation of that, I am clicking on this bus, and I am telling the MSB is 2 and LSB is 0. Means that is 2 down to 0. And I am selecting the output as O as an output, and even here I am selecting this as a vector 1 down to 0, and click on OK. Click on OK. So you will be getting the VHDL file under the design sources. Double click on that. The workspace will be opened, and here you can see the architecture is by default, and here just observe the port A is in, and that is of type std underscore logic underscore vector 2 down to 0, means A is now having the capability of handling 3 bits, and O is of type output and it is of 2 bits. That is the meaning of this. So this is the only difference, and whenever we are trying to write the program, just I am trying to show you the output of this program. So after this, see here, behavioral modeling means just in the process we'll be sending the input. So here the input is A, which is of type 3 bits, which is of 3-bit length. So here process A, and the process is begin if A is equal to 000. In the previous case it is a different. If A is equal to 1, B is equal to 1, and C is equal to 1, like that we did. But here, as the A is of type of is having 3-bit size, here directly we are comparing. So if A is equal to double quotes, and one more important thing you should note here is whenever you are giving the data stream, you should give the double quotes. Previously, whenever you are giving the numbers, you should give the single quotes. So this is the first line of the uh, truth table. So similar things we are doing here also, and the last case will be ending the last but one will be ending the else if else if, and finally the last row will be written after the else, end if, end process, and the behavioral modeling. So just after this I am just saving this program, and I will try to execute this, run behavioral simulation. So more or less, not more or less, the exact output whatever you got in the previous case, the same output you will be getting here. So whenever you are executing, you will be getting the waveform window. But observe here, this is like a bus. So expand this and give the inputs here. Right click, force clock, binary, leading edge is 1, trailing edge is 0, cancel after 2000 nanoseconds, and time period is 100 nanoseconds. You should go to the individual bits and you should give the output. You should give the input. Radix is 1, leading edge is 1, radix is binary, leading is 1, trailing is 0, cancel after 2000 nanoseconds, and the time period is 150 nanoseconds for the second bit. And for the third one, we are just giving it as uh, the time period we are trying to change it to 200. Leading edge is 1, trailing edge is 0, 2000 nanoseconds, and here we are giving the time period as 200 nanoseconds. And click on this, execute, and you will be getting the output. For seeing this output, just click on the zoom fit and expand this also. Expand this output which is containing 2 bits, and you can drag the yellow button like how we did in the previous cases, and you can verify all the waveforms. So you can undock this, and you can verify by dragging this cursor. You can verify the output of the full ladder, means by keeping aside the truth table with you. See, one important difference what we can observe here is whenever we are changing this modeling, means the way of writing the program. See, after simulation, what we used to do, we used to open the elaborated design. Just click on that, click on the elaborated design. It is opening here. Once it is opening, just we will observe how the schematic looks, how the schematic is looking in this case. So I am clicking on the open elaborated design, and I am waiting for the system to finish the process. And here you can see the RTL schematic is different. So the way the RTL schematic looks is related to the program what we have written. So whatever the modeling you are changing accordingly, or the programming style you are changing accordingly, RTL schematic will be changed. And the third output will be run synthesis. The synthesis report will be coming. So the first run simulation waveforms and these synthesis reports will be same. The only schematic will be changed for the different programming levels. So in this video we covered the behavioral modeling of the full adder, and the same behavioral model I covered in the two different ways of writing it. And the only change we observed here is uh, the RTL schematic, and the remaining things remains the same. And in the next video, I will try to cover the structural model of any of the logic circuit. Thank you all.